This is going to be a talk I've entitled Glitches in the Embedding Matrix. And this work is that I'm going to primarily be talking about is in collaboration with Sander, who's here in the audience, and also Pavel. And so to begin, I want to address this question: what is tokenization and why do we have it? Because this is going to be critical for understanding sort of the motivation behind some of this work. And first I want to propose a definition of tokenization that I'll be operating with. So I take tokenization to be the segmentation of a continuous input into items that are in a model's vocabulary. Language models can't take raw text as their input. Instead, we need to chunk them up into tokens that the language model has seen before. And tokenization in the domain of text can be words, parts of words, characters, or UTF-8 bytes. And in other media like images, it might be pixels or groups of pixels. In audio, it might be things like waveform segments. And all of these things can fit into this definition I'm proposing of tokenization. And the earliest form of tokenization is word-level tokenization. The most coarse sort of version of this is white space tokenization, which was used in early naive Bayes classifiers in TF-IDF. And how this works is you just take a string of text and you split along every white space. So your tokenization would end up looking something like this. Some other word-level tokenizers use simple rules, so they might split also on punctuation and contractions in addition to white spaces, and this is generally how NLTK and spaCy do this. So if we take a string like this, didn't will be segmented within that word into two tokens along that contraction, and also punctuation will be separated, unlike the earlier version. And so your final tokenization might look something like this. Some challenges with this are that this requires a very large vocabulary. So English has approximately 1 million words, depending on how you count it. Even with 50,000 or 100,000 vocabulary words, you're gonna, get most things, but anything that's not in the vocabulary is just gonna be UNC or unknown. And this is sensitive to things like capitalization. So if you have apple in your vocabulary, lowercase apple will get tokenized as apple, but capital A apple will just be UNC. It also will be sensitive to inflection. So if you have apple in your vocabulary, apples is going to be an UNC. Also, this is not going to be robust to misspelling. So if you have language in your vocabulary and you spell it langouge, like I often do, that's going to just be UNC. And finally, this is just not going to be able to handle new and borrowed words. So words borrowed from other languages or new words which are always popping up. And a solution to this solution to this is to use sub-word tokenization. So instead of taking whole words, we take word pieces. The most frequent items can be stored whole in the vocabulary, and we can use smaller chunks to make up less frequent words. And we can have, this allows us to use a smaller vocabulary for the same coverage. And in the worst case, new words can just be broken down into their bytes or characters. And so we'll never get UNCs with this kind of approach. So for this apple example, if apple is in our vocabulary, we can make up apples by adding an extra S token, or we can break down capital A apple into multiple tokens. Similarly, if we have misspelled words, then they might just get broken down into whatever smaller components are in the tokenizer's vocabulary. And probably the most popular subword tokenizer is byte pair encoding, or BPE. This is developed for machine translation primarily, and it consists of two main parts. So you have a vocabulary list and a list of merges, and individual bytes are merged in the order that they were learned in order to create the tokens in the vocabulary. Just to give you like a look into what this looks like. So this is what an actual like merged list looks like in a tokenizer. So this is the beginning of the list. So our most frequent pairs are T and H and I and N, and further down the list you get longer chunks that are being merged together. The vocabulary list looks like this. So you have your vocab items and their indices. At the beginning you have your special tokens and raw bytes, and later down the list you have sort of more meaningful looking words and subwords. Before I dive into just a bit more explanation about BPE, there's a secret step before all of this, which is pre-tokenization. And in this step, raw text is first split on usually white spaces as well as punctuation and contractions, like those previous word level tokenizers I was talking about before. And any merges that are learned are not allowed to take place across those pre-token boundaries. So if we have this pre-tokenized string, it will get broken down into individual bytes, and any merges, any tokens that come from that will not cross those boundaries. So just to work through an example of how byte pair encoding looks, we take a word like discombobulate. It's first broken down into individual bytes, which are here just characters for ease of reading. In the first step, the most common, the most frequent pairs of bytes are merged, and then eventually bytes are merged with already merged chunks, and you eventually merge things until you get your sort of biggest tokens, in this case discom and bobulate. Yeah, and so this is usually implemented at the byte level. It can also be implemented at the character level. So sentence piece is an example. Their BPE implementation is at the character level. And one of the consequences of the way BPE works is that you need these intermediate tokens in order to execute all of these merges. So going back to this discombobulate example, first we need all of the individual bytes in our vocabulary, and then for each merge, whatever the pair is merged into, those also need to be in the vocabulary. And so in total, to get this to tokenize this word, we not only need discom and bobulate in the vocabulary, but we need all 20-something tokens here to be in the vocabulary. Another consequence of this is that multi-byte characters are going to do some kind of weird things. So byte pair encoding usually operates over UTF-8 bytes. In this system, Latin characters or ASCII characters are represented with a single byte, but other writing systems usually require multiple bytes to represent a single character. So here's a kind of like schematization of that. So your Latin A just has a single byte. Greek letter might need 2 bytes per character. Chinese characters often take 2 or 3 bytes to represent, and then sort of ancient writing systems, also emojis generally require 4 bytes per character. I've kind of, I refer to this as a byte premium effect. That was in this paper from earlier last year. And so a tokenizer, a BPE tokenizer, in order to handle these multi-byte characters, can't just merge 2 whole characters. It must first take the bytes and learn merges between all of the bytes to make up the characters, and then you can have multi-character tokens that are merged from there. That means that it's actually possible for a tokenizer to learn merges that leave incomplete UTF-8 sequences. So for example, if this tokenizer doesn't learn this merge indicated by the dashed line, then the entire first character is just going to be undecodable. It's just going to appear as question marks. Similarly, if a tokenizer learns a merge like this, which crosses a character boundary and is composed of 2 incomplete UTF-8 sequences, then you're gonna end up with more undecodable bytes, and those can actually have some really crazy cascading effects and sort of lead to really long strings of undecodable sequences, which is really bad. So we've got these problems I've outlined with BPE. So we have this intermediate token problem, and we've got this stranded bytes and undecodable string problem. And so, these can lead to some unpredictable model behavior. And these kinds of behaviors have been talked about in the context of glitch tokens. So some of this, talk about this paper, Fishing for Magic Carp, which is by Sander, who's here in the audience. This isn't the first paper to sort of use the term or talk about glitch tokens, but has some sort of helpful examples that we'll be talking about here. So glitch tokens are often undertrained tokens, so they have a really low frequency in the corpus, and their embeddings aren't trained very well. So these are indicated in the lower left-hand corner of this plot here. And as I said, this can lead to unpredictable model behavior. Just to give an example of what this looks like, these are some identified glitch tokens in different models. So probably the most famous example is this solid gold magic carp token. Also a kind of quite common one is $ postal codes NL. And so these, just if you're wondering, these are like, they can come from usernames. This was like a Reddit username, or common strings from spam and advertising from web text, individual UTF-8 bytes, or just noise from like messy web data, things like this and this lorem ipsum string with some other stuff. And as part of that paper, Sander maintains this really beautiful repository of glitch tokens for pretty much all open models. So I really recommend checking this out, either for models you're using or just out of curiosity. So just to like illustrate what these glitch tokens can do. So this is what happens when you prompt Quen, I think 2.5, 7b with a slight variation on that postal codes glitch token. So this is not a glitch token. You get a model output that's sensible. Now when you actually give it the glitch token, then you get something much less satisfactory. There's this line in the middle that's kind of going crazy. So yeah, this is what happens when you get glitch tokens. So how do we fix this? I think a common sentiment in the field is maybe like, let's just get rid of BPE or tokenization altogether. And this has led to this tokenizer-free language modeling approach. Usually, so this was, I think, introduced by this paper from 2019 and has been since used in some of these other papers more recently. And what people mean by this is usually byte or character level language models. So instead of getting like multi-character subword tokens, the model just operates directly over bytes or characters. Under my definition of tokenizers, which I provided at the beginning, this isn't actually tokenizer free, it's just byte level tokenization. So I'll refer to it as tokenizer free. Some of the advantages of this are that you can use like a very small vocabulary size, which leads to fewer embedding parameters that you need to train. So if you operate on bytes, there's only 256 of them, or if you're using character level, you can pick some subset of Unicode characters. And so like you can also not have any uncs. Some of the cons, I think main reasons why this isn't really caught on very much, is that you get extremely long context lengths. So like most tokens are often 4, 5, 6, many more bytes long. So you're multiplying your sequence length by at least 4 or 5. And as memory requirements increase quadratically with sequence length, this gets expensive very fast for both training and inference. And then also, going back to this byte premium idea, this becomes even less feasible for languages with non-Latin scripts where each character has multiple bytes. So now you're maybe talking about a factor of 2, 3, 4 increase in context length on top of that. So that's, I'd say, the main limitation of this approach for now. One sort of like recent advancement in this area is the byte latent transformer architecture, which was proposed earlier this year, I think, by Meta. So this architecture operates over bytes, which are dynamically grouped together into patches. I've highlighted one in red. And, in practice, this is just tokenization, either like neural or context-dependent tokenization, something like that. And in the end, the actual transformer sees embeddings for those patches, which are conceptually indistinguishable from subword token embeddings. So I think, for now, maybe we don't have the infrastructure to take this like tokenizer free or sort of this patching approach. How can we prevent glitch tokens within the context of BPE? So that's what I'll be talking about for the rest of the talk here. So I'm going to talk about two main proposed methods. So the first is vocabulary pruning, and the second is constrained merges. So first I'm going to talk about vocabulary pruning. So this is basically a procedure in which you remove tokens from your vocabulary. Often you can remove extremely low frequency tokens. However, this could remove those intermediate tokens that we need in order to execute merges and create bigger tokens. So going back to this discombobulate example, say we identify ulate as a sort of token that we don't really need. If we take it out, then it means we can't merge and create that larger token. And now instead of 2 tokens, discombobulate gets tokenized into 4 tokens. And this is harming compression. So now you've just doubled the sequence length of this word that the model will see. So this was the inspiration for this paper, BPE Gets Picky, which we presented at EMNLP last year. And so we're wondering, like, what can we do? Can we prune the vocabulary, prune out these sort of like unnecessary tokens that are not seen very much during training without encountering this problem of getting in the way of the merges? So this is the main example we have in the paper. So if we have the word Kentucky, which is in the end merged with K and Kentucky, the intuition is that Kentucky is one of these tokens that you're not seeing very much outside of the context of Kentucky. It's basically only there to merge and create this bigger token. And to identify these cases, we propose this metric intersection over self, which is a relationship between the frequency of that the Kentucky token and the the frequency of the larger token that it's part of. And so if we look at these other tokens, ent and ucky, that make it up, they're occurring in other contexts, like ent might be in entropy and ucky might be in lucky, in other words. So these are occurring in other contexts, and therefore their intersection over self doesn't meet our threshold. But we basically identify this threshold at which we want to get rid. We identify these intermediate tokens that we want to get rid of in the vocabulary. I want to walk through just another example to sort of build up the intuition about this. So if we think of the subword OULD, which is in the word wood, So if we're building our list of merges in our vocabulary and we're learning the merge W and ood, we can make up would, but OULD, ood is still happening in other contexts, so we don't take it out of our vocabulary. Then we make the token could, and the intersection over self goes up a little bit, but still this is occurring in other contexts. And then finally, when we learn the word, the vocabulary item should, now we don't have as many contexts in which ood is happening outside of would, could, should, and the intersection over self reaches the threshold and we remove it. And the way we actually operationalize this is that we learn an additional list of tokens that we're removing, but we don't actually take them out of the vocabulary. We use them to execute the merges, and then if they are still there in the final tokenized text, they're unmerged into their composite tokens. So if you got, let's go back to, if you got Entucky in the final tokenized text, it would be broken down into ent and ucky. Yeah. Oh, there it was. So we looked at some of the effects of this. So we found that our prune tokens tended to have low frequency and low L2 embedding norms. So those are the ones in orange at the bottom left of this plot. So these seem like tokens that would be likely to be undertrained and become glitch tokens. We also wanted to just check that this wasn't harming other things that we knew might be important. So we looked at the compression, and we found that compression was pretty much the same, maybe even very slightly better with Picky BPE. We also trained a translation model with this tokenizer, and we found that performance pretty much stayed the same or even improved very, very slightly. So this is good. This indicates that Picky BPE isn't like harming other aspects of the tokenizer that we weren't trying to affect. So this seems pretty promising, but no one's trained a language model with it yet. Maybe I hope that will change in the not too distant future, but there's a bunch of engineering that we need to sort out and then to make that happen. So that was the first method for preventing glitch tokens. So in the context of vocabulary pruning, I talked about our proposed Picky BPE method. Now turning to the constrained merges approach. So basically, going back to these examples we were talking about before, we want to constrain the merges that the tokenizer can learn to prevent it from learning merges that lead to these incomplete partial UTF-8 sequences. So going back to this example from Chinese earlier, we want to prevent a tokenizer from learning merges across those character boundaries that lead to these undecodable sequences. So that's the motivation behind this paper. BPE stays on script, which we'll be presenting in just a few weeks now at the tokenizer workshop at ICML. And so in this paper, we first propose script encoding. Script stands for script category representation in pre-tokenization. And this is an alternative to UTF-8 encoding. In this encoding, each character is represented with 2 tokens of these kind of bytes kind of equivalent. The first token is a block token, and this indicates which script group the character is from, and we have an index token which indicates its index within that block. So for a letter, for like the letter K, this is maybe an example of what this would look like. You have your block token that represents it's a Latin character, and then you have some index token that represents its place within that block. And these are the different blocks. So most of the blocks have, around 1,000 items or less. Then we have our quite large groups, like the Chinese character group Han at the top has almost 100,000 characters. So we have multiple blocks for those like larger script groups. So comparing how this looks across different writing systems, where UTF-8 has variable byte length, like we talked about before with the byte premiums. Script encoding has always 2 tokens per character. So this gives us actually, as a byproduct, an equitable representation of different scripts within this like encoding standard. So that's also kind of nice. Then we can use this script encoding to create a constraints on the merge rules that we want our tokenizer to learn. So now we can say, okay, we just don't want a tokenizer that's going to learn a merge between an index token followed by a block token. We always want it to be a block token followed by an index token. So this would not be allowed, and instead, if you want to merge these 2 characters, the tokenizer has to first learn to merge the 2 tokens within each character and then learn a merge after that. So this constrained merge, this merge constraint can also be applied to regular UTF-8 encoding with other pre-tokenizers. So CL100K and O200K are the OpenAI pre-tokenizers. And we found that the constraining the merges does significantly reduce the number of partial UTF-8 sequences. So that's the right column is the constrained one and the left one is unconstrained. But if we add the merge constraint and our script BPE, we completely eliminate partial UTF-8 sequences with our tokenizer. Though we'll note that you need to, the script encoding by itself doesn't solve this problem. It's the combination of the script encoding and this constrained merges that leads to the elimination of these partial UTF-8 sequences. Again, we want to just make sure that this doesn't affect other things, so we check the compression, and so the constrained merges have equal or better compression sort of across the board, so it's not making our sequences longer. We also want to make sure that this is something that we can kind of feasibly use. I sort of alluded to this before, but the picky BPE method, the way we implemented it, is really, really slow. So that's something to kind of keep in mind. It turns out that constraining the merges actually speeds up training with our script encoding. So it's actually faster training than the UTF-8 plus OpenAI pre-tokenizer, which is kind of nice. Right, so that's our proposal for constrained merges, has to do with this script encoding. And now I'm gonna just, in the last few minutes here, introduce a secret third thing that you can do to prevent glitch tokens, which is just to train a custom tokenizer on in-distribution text. Because these other methods that I've mentioned are sort of still works in progress. I've mentioned they're not quite ready to train language models on. But in the meantime, the easiest thing you can do is just to train a custom tokenizer. So it's pretty common practice to just reuse an existing tokenizer. In fact, I see that kind of recommendation on like tutorials and stuff, just taking a tokenizer from Llama or whatever it is and reusing it. The problem is that this really increases your chance of getting undertrained and glitch tokens, especially if you don't know what the training distribution of the data the tokenizer was trained on. Maybe the tokenizer has things in its vocabulary that are just never going to appear in your training data, and that's going to lead to undertraining and glitch tokens. This also just tends to lead to worse compression. I have found just through like testing, and that means you're also going to have longer training time and slower inference. Depending on your setup, it takes somewhere between seconds and hours to train a tokenizer. It's generally pretty easy to do with the Hugging Face tokenizer package, and it doesn't require any GPUs. So it's way easier than the other things I'm proposing here. And this is, yeah, just probably the easiest thing you can do to prevent these undesirable behaviors that come from a tokenizer. I will say, as a caveat, we do need better documentation and infrastructure on this point. Sometimes it is a little confusing to navigate the Hugging Face tokenizers package, and there's maybe things that are not known. I think also just like the study of tokenizers is still developing. Like we don't understand really what the effects of these sort of core training choices are. Like, how much data do you need to train your tokenizer? This was basically just a decision that was made kind of arbitrarily, or that was passed by like word of mouth. A recent paper did look into this. So this group, mostly at Kensho. I recommend this paper. It's super interesting. They looked at like what the effects of different tokenizer training data set sizes are. To my knowledge, this is the first paper like this, so I think we need more papers like this so we can know how best to train our tokenizers. Yeah, there's other kind of missing information, like other things like how does choice of pre-tokenization method affect tokenizers? There's all kinds of things we don't know. So, you know, I think tokenization is a very interesting research area, and we have a lot of work to do. Yeah, so that's actually all I've got. So we've got plenty of time for questions here.